Combinatorial Explosion. This is R&B. They just moved into a new apartment. R&B want to decorate the wall over their fireplace with a string of lights. Each light in the string will be either red or blue, since those colors are R&B's favorite colors. R&B can program each light so it displays either red or blue. They want to vary the colorings so that they can have a different coloring of red and blue lights each day for as long as they live together. Assume they will live together for 75 more years. Under that assumption, they will need 27,375 different colorings. Note, for simplicity, this omits leap years. How many lights do they need on the string of lights to have a different coloring every day for the next 75 years? Starting with level 1, let's see how many colorings are possible at each level until we find a level with enough lights to meet R&B's need for variety. Level 1 yields only 2 possible colorings. Level 2 yields only 4 possible colorings. Level 3 yields only 8 possible colorings. Level 4 yields only 16 possible colorings. Level 5, 32, Level 6, 64, Level 7, 128, Level 8, 256, Level 9, 512, Level 10, 1024, Level 11, 2048, Level 12, 4096, Level 13, 8192, Level 14, 16384, Level 15, 32,768. So a string of 15 lights yields 32,768 possible different colorings of red and blue, which exceeds the 27,375 needed. Here's the formula to calculate the number of possible colorings for any given number of color options and lights. Just remember that in this type of equation, C represents the total number of potential options for each occurrence of the object that will contain the options. In this example, C equals 2 because red and blue are the only options. If R&B added a third color, say green, then C would obviously equal 3. The exponent x represents the number of objects that will contain one of the options, red or blue, in each different coloring. In this example, those objects are lights, so as you noticed, for a string of 15 lights, x equals 15. As you see, an increase in the number of lights increases the number of possible colorings exponentially. Therefore, it does not take many lights to get to a very, very large number of possible colorings. For instance, how many possible colorings of red and blue do you think there are in a string of 100 lights? That's a very large number. To give you some perspective, the total number of atoms in the universe is estimated to be between 10 to the 78th and 10 to the 82nd. So a string of 100 lights yields an amount of possible different colorings of red and blue equal to almost 40% of the total number of atoms in the universe. That's why this type of problem is called a combinatorial explosion.